I want to kind of shift gears here and move from these kind of econometric natural experiments that focus on causal estimates to longitudinal data used in a much more conventional way for developmental psychology. And that is with a variety of change models in effect. All right, so I tried to list some of the models that are out there. Simple change is the most direct one. There's something called a residualized change model, which is also called a lag-dependent variable model, sometimes called a cross-lag panel model. There are some variations, but by and large, these are very similar. Latent growth model, we talked very briefly about toward the beginning of the class. And I want to add two more. One I call Greg's instantaneous change model. And the second one is Greg's accumulation of inputs model. All right, so we've got a little bit of explanation coming up. Let me try to characterize these with equations, right? By simple change, suppose we have just two observations, time 1 or time 0 and time 1. Right, so the same people, the same kids, the same schools are observed in a longitudinal study that only lasts, has 2 waves, and we're just calling those time 0 and time 1. So a simple change model would have some dependent variable, y, at time 1, minus that same variable observed at time 0. All right, we're just subtracting for an individual. Think of the ECLSK data. You've got kindergarten and first grade test scores or teacher reports of socio-emotional behaviors. We're just taking the 2 reports of socio-emotional behaviors, 2 different teachers, and we're subtracting them. If it's a test score, we're just taking the 2 test scores and subtracting them. So simple change is some function of an X variable of interest plus controls, other controls. Okay, so seems simple enough. Residualized change models aren't that different. They're of the form y1, in other words, the second measure of y. We'll call it c plus d1 x plus d2 controls. Plus d3 y0. In other words, y0 was on the left-hand side in the first model, and we've just taken that y0 and moved it over to the right-hand side. Now, so it's pretty obvious why this is called a lagged dependent variable model, right? The dependent variable is y, and we're measuring or we're regressing this y1 on a lagged version of y0. Residualized change, I knew at one point years ago why it was called residualized change and forgot. So if you really are curious, you can look it up and let me know. Now, cross-lag panel models tend to look like y0 affecting y1, x0 affecting x1, and then we have these cross paths where y0 is affecting x1 and x0 is affecting y1. So these are, this could be a SEM model. But as I tried to explain early on when I talked about mediated models, when you see this, you can do a single SEM model, or you can break it up into separate equations where every variable with arrows running to it is a separate equation. All right, so y1 has arrows running to it, and the equation is y1 a plus b1 x0 plus b2 y0, right? y1 is a function of x0 plus y0. And then these paths represent the coefficients on these arrows. So b1 is the coefficient on x0 predicting y1, controlling for y0, and then b2 is going to be the coefficient on y1. On y0 is a predictor of y1 controlling for x0. All right, everybody with me so far? Now this looks a lot like this, right? You could think of adding controls down here, affecting y1 and x1. And you still have this x1 equation that we haven't talked about. But in terms of the dependent variable we're interested in, which is y, we could add controls here. And then we've got something that's pretty much identical to this, right? So a lag dependent variable model and then the y part of this cross lag model are essentially the same thing. You're sticking, in contrast to this, you're sticking y0 on the right-hand side of the equation. Okay. Now, what's the difference between these two? Well, let's add y0 to both sides of this equation. Right? Then over here, we're left with y1, a plus b1x plus b2 controls plus, and it's not, a coefficient times y0. Here, if it's y1 minus y0, the implicit coefficient on this term is 1. No, we're not allowing it to be anything other than 1. So it's really constraining this coefficient to be 1 times y0. So this change equation is like a residualized change model, except instead of having the coefficient on y0 be estimated freely as a D3 in this equation, you're forcing it to be 1. And indeed, in Stata, you can easily specify fixed values for coefficients. If you run y1 as a function of x controls and y0, and force this coefficient to be equal to 1, you'll get exactly the same A, exactly the same B1, exactly the same B2 as you do when you run the change model. All right, so what, as a practical matter, how would you choose between constraining a coefficient to be 1 or allowing the coefficient to be estimated as part of the regression? There's not a good answer to that. I mean, simple change is rarely used because people worry about change measures having a lot more error than level measures. So this residualized change model ends up being preferred, where you're sticking y0 over on the right-hand side. But you know, as we'll see when I talk about these models down here, there are conceptual models that would lead you to prefer simple change, and that would lead you to want to, if you do put y0 on the right-hand side, constrain the coefficient to 1, right? So I'm just going back to the simple change here. So we'll talk about that in about, I don't know, half an hour or 45 minutes or so. But these two are obviously very similar. And as we saw, they differ only because this is allowing the coefficient in y0 to take on whatever value the best fit dictates. And up here, implicitly, if you put y0 on the side, you're forcing the coefficient to be 1. All right, so when I talk for a while and don't hear questions, I start to worry. Let me pause for a couple of questions.
I had a question about the residualized change model.
Sure.
So I see that, but X1 is not, you wouldn't want to see the effect of X1 on Y1?
I'm sorry?
We wouldn't care about the effect of X1 on Y1?
Oh, well, there is no path running from X1 to Y1. With the cross-leg panel models, there are only these 4 paths, right? So, you know, if you have this model, you add a 5th path, that's a very, very different model. It's, you know, this plus B3 X1, you're saying that there's some sort of contemporary effect of X1 on Y1. And putting that in is a very different model from leaving it out. So I'm just trying to draw the parallel. If you do leave it out, and all cross-leg panel models do leave it out, you have paths running from X0 to Y1 is B1, which is directly comparable to this residualized change model we just talked about.
Is there a reason why it's left out of the, because if you have longitudinal data for X1, wouldn't you want to have it be part of your model? I guess I'm not really understanding why we wouldn't want to include it.
Yeah. So, you know, invariably, you throw a lot of information potentially available to you away. That's especially true for these natural experiments, right? Where you're throwing away enormous amounts of data in order to isolate the variation of interest. In this case, it all depends on your theory. And, you know, usually people are fine with some past value of X or Y affecting some subsequent value of X or Y. But, you know, if you draw either an arrow going up here or an arrow going down here, you're adding in something extra. And it's saying, in this case, that Y is a function not only of past Ys and past X's, but it's also a function of X at the same time Y is measured, right? And that's a very different model.
Okay.
So, it's very hard to talk about these models outside of the context of a specific example or a specific kind of developmental process. And that's exactly what I'll do when I talk about instantaneous change models and accumulation of input models. But think carefully. It's always important when you're thinking what regression to run a regression that is in accord with the kind of theoretical thinking that you've got.
Mm-hmm.
And rarely do people have these kind of simultaneous influences. If they've got longitudinal data, it's usually always, what's true now is a function of what used to be true for both X and Y variables. Go ahead.
Yeah, but a change would be okay, right? So like we saw in the quality care that they're doing the change from time 0 to time 1, like that's more appropriate in that case.
Well, and we'll talk about this in the childcare article. It was change on the left-hand side, not as a function of X's. And you notice I haven't put a 1 or a 2 here, or a 0 or a 1 here. I haven't put a 0 or a 1 here. I'm leaving that a little bit vague at this point. In the context of a cross-like panel model, it's very explicit. It is X0. But depending on the model, it could be initial X, it could be an average value of X between 0 and 1. That's the accumulation of inputs model we'll talk about. So I'm leaving that a little vague now. But people, they really want to try to approximate causal models whenever they can. And for good reason, people are a little bit leery of saying Y1 is a product, kind of an instantaneous product of X1. Past X's are okay. But this, you could have X causing Y or Y causing X, and putting both in at the same time with X1 predicting to Y1, let's say, or vice versa. That starts to smack of what is called simultaneity bias, where you're trying to estimate a concurrent relationship between two things, and that's very difficult to do. You have to have very strong theory for that to be the case, and it's usually the case that theory, may say what you've become in terms of X might predict Y, but it's often the case that you can turn around and make the same argument that where you are with X is a product of where you are with Y. And that's what people tend to avoid by not putting this arrow in and having everything be predicted from the past.
I see. Thank you. That makes sense.
Sure. One more question. If you were here in person, I would stare you down. I know people have questions. You're reluctant, but don't be reluctant. What the question that you have is a question that almost everybody has.
I just have a really quick, fast, simple clarification question.
Sure.
So simple change is specifically for change over time, and then difference in difference is a change, but at the same time?
What difference in difference can be across time, but it's usually at the same time. But
So
it could be both. It could be both.
right. So I don't quite understand the difference then between simple change and difference in difference, if difference in difference can also be across time.
Well, think about Curry and Walker with correctly interpreted coefficients. That had a component of a temporal component. It was changed before and after Easy Pass came in, right? But then it also had a contemporaneous component because you were comparing births to mothers who lived within 2 kilometers and then to mothers who lived between 2 kilometers and either 5 or 10, right, depending on the model. So it mixed those things together. And it's a much more complicated model than these kind of simple models are, right? So it's best to, for difference in difference, it's best just to focus in on what the differences are and how do you set up a model, an interaction model in the case of Curry and Walker, that captures exactly the sets of differences that you want, whether they're temporal differences or whether they're concurrent differences. So it's best to kind of think of those separately. And indeed, one of the beefs that I have with these kind of developmental models is that they've been developed in a totally atheoretical kind of way, right? They've been developed by statisticians and they've got interesting statistical properties, but they haven't been developed for solving a particular set of conceptual models, estimating a particular set of conceptual models in mind, right? And if you think about Curry and Walker, the model that they developed is exquisitely tailored to the nature of the data that they have and the sources of identification for these effects of congestion on birth outcomes, right? So in contrast, if you think about, there's kind of a research question. Everybody has these research questions. And one path that economists take is to develop a conceptual model that generates refutable hypotheses. And then choose the statistical model and then conduct the analysis. So economists tend to take this path and then continue on down. Developmental psychologists certainly have research questions. They have, very well-defined thinking about nature of developmental processes, but rarely, think of Bronfenbrenner and the circles, the concentric circles. That can accommodate a thousands of different hypotheses, right? Some of which are contradictory with one another. And so rarely do developmental psychologists take the step of a very concrete model that generates refutable hypotheses. And they just jump right to the choose a statistical model, right? I've got longitudinal data. Let me do a latent growth model. Let me do a residualized change model. Because people estimate those kind of models, and I've got data that can be used in those kind of models. But leaving out this step has its costs. And I don't know, maybe I'm being defensive about economists, but economists have a lot of very well-developed theoretical models that are often based on very simplistic assumptions, so-called economic man, Homo economicus, rational in every way. It's criticized, right? Because people are obviously not rational in every way when they make decisions. But that's not the point. The point is that if you start with some simplifying assumptions, can you generate predictions that you can actually then take to data and see whether they hold up or not, right? And the idea is, a theory is as good as its predictive power. And the better it is at predicting, it doesn't make any difference how realistic it is. And you don't want to be too extreme here. But you really want to know to what extent the model generates hypotheses that seem to hold up when you actually go out and test them. And you don't see much of that in developmental psychology. So that's why when we did the childcare paper, we laid out this, what amounts to an accumulation of inputs model, and developed the estimating equation from that. And it was, well, let me keep going here. Latent growth models we'll talk about a little bit later in the class. Instantaneous change models, if you got longitudinal data, look like this. Y1 minus Y0 is a function of X1 minus X0 plus controls. So that's starting to look like more like that with that arrow. But accumulation of inputs is also has simple change on the left-hand side. But now the X that gets stuck in here is the average value of X between times 0 and 1 plus controls. So it's not just X1, it's not the difference between X1 and it's not just X0. It's not the difference between X1 and X0. It's kind of the average value of X between times 0 and 1. And
excuse me.
Yes.
Is this supposed to be Y1 minus Y0 equals C plus D1?
You mean,
It's
should this
currently
be a
Y.
1?
Yeah.
Thank you. Yes.
No problem.
I mean, we've got change up here. We've got change here, change here. All these are the same, Y1 minus Y0, right? Over here in simple change, we had kind of a generic X. We didn't say whether it was X1, X0, or something in between. Instantaneous change, we're very specific in saying Y1 minus Y0 is a function of change in X plus controls. And then in the accumulation of inputs model, again, it's simple change, but now we've got not change in X, not initial value of X, but the average amount of X between times 0 and 1. And that turns out, we argue, to apply well to a situation where you're interested in the effect of childcare quality on children's cognitive development. So shouldn't be obvious from this, but that's where we're going to next. But I just wanted to kind of lay out the territory here before we launched into these conceptual models. Any questions? So, I mean, the issues are, if you've got longitudinal data, should you be sticking the initial value of your dependent variable over here on the left-hand side as a simple change? Should you be sticking it on the right-hand side? I erased it, but that was the residualized change model, lag-dependent variable model, with a coefficient that was estimated as part of the estimation process. And, you know, that's one issue. And then the other issue is, which X's do you want? Do you want change in X? Do you want average value of X? Do you want initial value of X? You know, as this lag-dependent cross-lag panel model would call for if you leave this path out. Those are not, you can't say for statistical reasons that one of those models is preferred to other models. It all depends on what question you want to answer. Okay. So start with the question. Ideally, start with a fairly well-developed conceptual model that generates refutable hypotheses, and then figure out which of these various statistical models, or what other model. If you think about Curry and Walker, it's yet another model, is going to be what you need to do the testing.
Greg, could you talk a little bit more about the difference between like those the simple changes and the residualized change models? In terms, I feel like I understand what's going on mathematically, but how like the interpretation in the simple change would be like if you go up or down points. But what about the residualized? Like, how would we interpret if we're controlling from Y0? Or a little bit more of that difference?
You know, it's a great question. And I don't know the answer. You know, the lagged change was V2 controls plus V3 Y1, right? And I'm about to go through this accumulation of inputs model, you know, which suggests you should have Y0 on the left-hand side with a simple change as the dependent variable. If you stick it over on the right-hand side and allow its coefficient to be freely estimated, you lose the correspondence with the interpretation of the accumulation of inputs model, right? So I don't know what it means. I don't know what an effect or an association between X and Y controlling for, I'm sorry, this is Y0, controlling for Y0. I don't know how to interpret that. I know how to interpret it if you bring Y0 over here like this, but let me go through the accumulation of inputs model and you can see what that correspondence is. Now, that's not to say, you know, maybe the model that you're estimating makes the most sense if you put Y0 on the right-hand side and allow its coefficient to be estimated. There may be conceptual models where that is the most appropriate. But my point is that if your conceptual model tells you that's not appropriate, and you really should be sticking y0 over here and restraining its coefficient in effect to be 1. So you've got y1 minus y0. Then that's what you should do. Then everything becomes interpretable in light of this model that you're assuming to be correct. All right, so I think I need to develop the accumulation of inputs model and the simultaneous change model to add a little flesh to this. So if there aren't other questions, I will turn to that. You want a 5-minute break before I do?
Yes, please.
Okay. I don't know if I've ever asked that question and people have said no. All right, so it is do the instantaneous change and accumulation of inputs modeling. Now, again, these are conceptual models that I want to lay out and try to argue that they probably apply in some circumstances at least. And then once we've got the conceptual model down, then we can think about what the implications are for what the longitudinal change model looks like. All right, so instantaneous change. Let's think about kids in center-based childcare and behavior problems, okay? And for temperamentally sensitive kids, being in a center-based situation with kids running around all over the place, especially toward the end of the day, can be very stressful. There have been these interesting cortisol studies where you monitor the cortisol levels of 3-year-olds and 4-year-olds in center-based care. And for certain kids, you see the cortisol levels increase substantially toward the end of the day as they, start to lose it, and everyone starts to lose it toward the end of the day in childcare centers. So one consequence of that might be child behavior problems increasing as a result of this stress when kids are in childcare. So we might expect child behavior problem reports on the part of the parent or the teacher, let's say at time 0, to be a function of center-based childcare All right, this is a 1-0 in this case, whether in center-based childcare. And then control variables, let's call them observed control variables. And now we're going to add in unmeasurable or unobserved. Control variables, we'll just call those Z. So these Z variables can be both persistent, temperament, for example, and time varying. They're always present in analyses, right? You haven't measured everything. There are unmeasured influences. And, in this case, if you've got child behavior problems as the variable and then childcare as the dependent variable, childcare as independent variable, you really worry about these unmeasured characteristics Z, these omitted variables that are correlated both with the chance of a kid's being in center-based childcare and the child's behavior problems, right? So they're everywhere. They're part of every analysis. And one of the things that we can do with change models is reduce their effect. In fact, completely eliminate all the effects of persistent Z variables, even if they're unmeasured. Sounds miraculous, but let's see how that works. So if we just have a cross-section of data where child behavior problems are measured, a child being in childcare are measured, we've got controls we can control for, we've got the kind of classic selection problems, omitted variable bias problems, right? Being in center-based childcare is not a random event. There is choice going on. It could depend on the child's developmental stage, the child's temperament. And indeed, you know, suppose it is the case that being in childcare is associated with more behavior problems. It's kind of a persistent finding in the childcare literature that a lot of people want to sweep under the rug. It may be that when you run a cross section, you don't observe that. You know, suppose that selection into childcare by parents takes into account the fact that maybe their child isn't going to do very well in center-based childcare, so they're not placed in center-based childcare, right? Only the kids who can really handle the hustle and bustle of center-based childcare are in childcare, in which case the kids in childcare, their behavior problems are likely to be no different from the kids who aren't in center-based childcare. So even though there is this relationship, it's not going to show up if you just have cross-sectional data. If you've got longitudinal data and can think about child behavior problems, say, a year later, governed by the same process, if we just had a cross section at time 1, we'd have the same estimation problem that we've got at time 0. But now, if we've got longitudinal data, let's do the subtraction. So subtracting, we have child behavior problems at time 1 minus child behavior problems at time 0 is a function of, let's ignore the constant term, B1. We've got B1 childcare 1 minus B1 childcare 0. So that's B1 childcare 1 minus childcare 0. Plus controls, B2, it's actually change in controls now, plus 0 for persistent Z's, right? If we've got a Z variable, let's say it's genetic predisposition, it's some sort of long-run measure of parent socioeconomic status that we can't measure very well. Any sort of persistent influence on child behavior problems is going to be differenced out of this equation, right? Which is a huge benefit. We have omitted variable bias from Z up here. We have omitted variable bias from Z here, if we treat these as a cross section. But if we can difference them, we difference those two things out to the extent that Z is persistent. So estimating this change equation is not subject to the kind of omitted variable bias from persistent unmeasured characteristics, Z, that the level equations are. And moreover, and this is not a completely intuitive point, we get this longitudinal data, we run this equation, change is a function of change, and we get a coefficient, and that B1 coefficient has exactly the same interpretation as the B1s did in the level equation. Right, so up here, oh, go ahead.
I had a question about the B3 canceling out. So why wouldn't it be like plus B3 the change in C as it is for controls?
Well, we've got B3. You're talking about the Z's, right?
Yes.
B3 Z minus Z. So you still have B3, but to the extent that Z is persistent, that's 0. So it drops out.
So you mean persistent, like it's the same?
Yes,
Okay.
that, right, it's some unchanging characteristic of the child or the family or the neighborhood that is at work at both times 0 and 1 as a determinant of the child's behavior problems.
Okay, and the other ones don't cancel out because we're assuming those are changing for controls in CC.
Well, you know, if a child is not changing its CC, its childcare status, his or her childcare status, then they're not really adding any variation to this equation. So what makes this work is that some kids are changing from being in childcare to not being in childcare, or from not being in childcare to being in childcare, right? It's those changers that are driving the variation that this equation takes advantage of.
Okay.
You know, and if everyone is kind of persistently in childcare or not, then this isn't going to be a very effective technique because you won't have very many, you won't have any changers, so you really can't estimate this. But for most kind of situations, X variables of interest are changing over time. Kids are moving in and out of childcare all the time. And if change is persistent enough, pervasive enough, then you're able to get this estimate of B1.
Okay, thank you. So the difference is to reset myself. Would it be like then the C is the same, so that's why they cancel out, but the other ones are changing, and so is the case for the control variables.
Well, for control variables, if they're not changing, then they drop out too, right?
Okay.
But you know, let's say we've got income as a control variable. Family income fluctuates to some extent. So what would go in here would be the change in income between time 0 and time 1. Just as over here, you know, if this is a 1-0 variable, whether in childcare, and you subtract the two, then it's taking on values of -1, where they go from being in childcare to not, to +1, where they go from not being in childcare to being in childcare, and then the zeros are when the childcare situation doesn't change.
Thank you.
So it sounds like a very different equation, but you know, trust. Oh, let me put this up in red letters. Trust algebra. One year, my class bought me a T-shirt that just said "Trust Algebra" on the front. But you know, that's really what a lot of this is all about. We're kind of going conceptually through these equations, we're manipulating them in very simple ways, in this case, just subtracting one from the other. And we're getting something that looks very different. These are 1, 0 variables. This is a -1, 0, and +1 variable. The dependent variable looks different. This is change. But if you trust algebra, which I recommend, you would get out of this a coefficient on this change in childcare status that has exactly the same interpretation as these two level equations do. It's preferred because it's not being affected by the biasing impact of these unmeasurable persistent Z characteristics. All right, I know you've got other questions.
I have a question, but it's more about application of something like this.
Sure.
So in our example, could you describe what an unmeasurable variable would be in like the first equation that goes away in the third equation?
Child temperament, to the extent that it's it's strongly genetically determined, early temperament, and that genetic component of temperament isn't going to change between age 3 and age 4, right? It's a pretty persistent. Well, if it's genetic, then it's quite persistent. So whatever biasing effect there might be from hard to measure kind of temperamental features of the child, those are the same at the 2 points in time. They have the potential to heavily influence each of these level regressions, but they get differenced out when you look at the change equation. So, just think about what's going on. Let's say you've got temperamental kids and not temperamental kids. In each of these level equations, you're looking at variation across kids. Some are ending up in childcare, some not. Some have child behavior problems, others don't. But you're comparing across kids, some of whom are in childcare, some not, and you're looking at their behavior problem score. Change, you're looking at the same child, right? For the same child, is a child going from not being in childcare to being in childcare, increasing their behavior problems, right? And with this example, it's really come this interaction for temperamental kids, temperamentally sensitive kids. You'd expect changing into childcare would increase behavior problems. Leaving childcare between 0 and 1 ought to reduce child behavior problems, right? It's an instantaneous change, more or less instantaneous. So for these kids in childcare, behavior problems. Not in childcare, pure behavior problems. And the level equations aren't very telling for that because you're not comparing the same child in different settings. But if you have longitudinal data, then you can compare the same child in 2 different settings, provided that enough of them are changing settings. And so you get a much less biased view of the extent to which being in center care is affecting behavior problems.
Thank you. That makes sense.
Other questions? How about one more? Brian, help me out here. I know you've got questions.
Actually, I have a lot of questions. It's not actually, I'm trying to figure out the difference in between that and the residual change approach, right? And so something
question.
I'm like right there, but I just can't figure it out. It's something about So in this model, it helped me kind of understand, I guess, why it's called residual change a little bit. I guess something's regressing on between the control and the, it's like, I'm thinking, that's what I'm thinking. Something is regressing between the control and then I guess beta, I'm figuring it out in my head
So
right now. So
it's a totally different model. Residualized change, in other words, lag dependent variable, would
right.
have child behavior problem 1 as a function of C plus D1, child care probably 0. There's no change in child care typically in those equations, plus D2 controls, plus D3, child behavior problems at time 0, right? You're sticking the initial value of the dependent variable over here on the right-hand side, and that's totally different from this, right? This is, you're constraining, you're not allowing this coefficient to be estimated. You're constraining this to be simple change. And what the model says is that you shouldn't be putting an initial level of childcare. You should be putting in the change, right?
That's
if,
it.
you know, if you really think there's an instantaneous change process governing the relationship between childcare and behavior problems, then you want change on change. You don't want residualized change model. You don't want a growth model, as we'll talk about. The theory led you to exactly this equation. And if you try to do another equation, you know what, you don't know what, the theory told you B1 has an interpretation, right? So to get it, you estimate change on change, provided that this model is right.
Gotcha. Thank you.
Okay, so if no more questions, I'm going to punish you with the accumulation of inputs model, which is the one used in the childcare article. And I think is a much more universally applicable model for a lot of kinds of things that you're going to be working on. So let's do that. So this is accumulation of inputs. It's another conceptual model, very different from instantaneous change. It's saying where you are, in the childcare article, it was cognitive scores, let's say at age 5. And we're relating this to, instead of being in childcare quality. That's what the article focuses on. You could have this model for being in center-based childcare also. But we're saying, you know, cognitive development is not an instantaneously determined state, right? Behavior problems could be much more transitory, much more changeable with circumstances. But something like cognitive development, you know, a kid's cognitive development at age 5 is a product of a whole history of inputs to that cognitive development. So, you know, the kind of conceptual model, if you think about childcare quality, we want to add up childcare quality. I'll keep saying CC, but we're switching from being in center-based care to quality. Let's say from birth to age 5 of childcare quality, plus an accumulation of family inputs from birth to 5. Paul is doing a nice paper comparing cognitive stimulation in childcare with cognitive stimulation in the home. because that was measured in this data set also. So, you know, cognitive development is going to be a product probably of childcare quality in center-based care, but also probably more importantly of cognitive stimulation in the family all the way up to age 5, plus other controls plus other measured controls. And these are the unmeasured influences. So they're always lurking, these Z variables. In this case, if this is what you estimate and you've measured all these things very well, you've got to wonder, why is it that children end up with different levels of childcare quality, right? Income certainly matters, and you can control for some of that. But there are a lot of difficult to measure kind of parent preferences that determine childcare quality and that affect cognitive development, but they're just very difficult to measure. So because you can't really get a handle on what those things are, measure them and stick them in the equation, if you estimate this equation, you're likely to get a biased estimate of the effect of childcare quality because of these omitted variables. Okay, so far so good. So if this is holding at age 5, let's suppose it's a general kind of process that it holds at an earlier point too, age 3. This is this early versus late distinction in the paper, right? Early was up to age 3, late was age 3 to 5, roughly speaking. So if this is a general process, then we would expect it to hold not only at age 5, but age 3 as well. But now we're going from birth to age 3 instead of birth to age 5, right? Cognitive development age 5 was a whole history of inputs up to age 5. Our outcome here is age 3. So we've got a history of inputs from birth only up to age 3. And similarly, these family inputs are going from birth to age 3. We have other controls that you could measure. And we've got these same impossible to measure parental preferences, other kinds of, maybe environmental constraints on availability of quality care. You can think of all sorts of things that might be affecting why kids end up with different childcare quality. All right, so we've just taken a kind of conceptual model and we've said, what would that look like if we're developing a prediction for cognitive development at age 5 and age 3? Everybody with me so far? So now subtracting, we have cognitive development at age 5 minus cognitive development at age 3. So a simple change on the left-hand side. We'll leave out the constant. So now we've got B1, and we've got birth to age 5 childcare quality, and we want to subtract out birth to age 3 childcare quality. Right? So we've got birth age 3, age 5. At age 3, we've got childcare quality running from birth to 3. At age 5, we've got childcare quality running from birth to 5. If we subtract this from this, all we're left with is the childcare quality between ages 3 and 5. Okay, so B1 is multiplied by childcare, or is a coefficient on childcare quality running from age 3 to 5. So we're just averaging childcare quality between ages 3 and 5. We're averaging family conditions from ages 3 to 5. We've got these other controls. And again, we're differencing out the persistent determinants of cognitive development, right? Because we've got them in this equation, we've got them in this equation. And when we subtract this from this, it's B4, but it's Z minus Z, which is 0. So the nice thing, the wonderful thing about this change equation is that the influence of impossible to measure factors, persistent factors, aren't influencing your estimate of B1 here, right? And here again, this B1 has exactly the same interpretation as the B1s here do. So even though it's a different equation, you know, this is these are unit increases in childcare quality, averaged from birth to 5, averaged from birth to age 3. This is childcare quality average between ages 3 and 5. But because you've got change over here and because algebra works out, this B1 has exactly the same interpretation as those B1s. So, you know, what's happening here, cognitive development is a function of a whole bunch of stuff that happened prior to age 3, cognitive development at age 3. Once you do the subtraction, or you subtract out cognitive development at age 3, you're in effect subtracting out all of those prior influences because they're all absorbed by cognitive development at age 3. So this is a very powerful kind of equation because cognitive development is kind of the sum of all these influences up to age 3. And then you can just take off from there and say, well, what happens after age 3 as a function of what happens in terms of childcare quality after age 3, what happens to these other family, sorry, this is FAM, this is other controls, this is B4.
Can I ask a question?
Sure.
Why do we have to first have the cognitive ability for age 5, averaging birth to 5, and then cognitive ability for age 3 and averaging birth to age 3? Why can't we just from the beginning say cognitive ability 3 to 5 and then averaging 3 to 5? Why do we have to do all of that? It seems redundant. No?
Well, I'm supposed to profess about something, right? I'm a professor, so I might as well fill in the gaps with some discussion. That was a joke. So it's only this model that leads you to think it's obvious, right? But think about instantaneous change. If cognitive development was a function of concurrent childcare quality, then you'd get a change in cognitive development is a function of childcare quality at age 5 minus childcare quality at age 3, not average quality between ages 3 and 5, right? So this particular model that views where people are at one point as a product of past history, that particular model gives you this particular estimating equation. Okay, I don't see a light bulb above your head. What tell me what you still don't see.
Why do you said like, because I wouldn't end up with the average, I would end up with 5 minus 3, right? If I go with my way, right?
Well, I'm saying, so think about all the different models that we've talked about. We talked about simple change, which would have childcare quality probably at age 3 over here. We talked about residualized change, which would bring cognitive development at age 3 over to the right-hand side and would probably have childcare quality at age 3 over here. We talked about instantaneous change, which has change over here, but it's got change in childcare quality, not average level of childcare quality between ages 3 and 5. So all of those are very different, especially childcare quality variables. It's not initial level, it's not final level, right? It's the average level between the point of measurement of these two cognitive measures. So it's very specific. If the process that you're interested in isn't an accumulation of inputs type process, then this isn't the right model to go with, right? But I guess my plea is to go with some kind of model that makes sense. If you've got a residualized change model, which a lot of people estimate latent growth models. What conceptual model does that correspond to, right? It doesn't correspond to accumulation of inputs, right? It doesn't correspond to an instantaneous change model. I've never been able to hear an articulation of a kind of a theoretical interpretation of what would lead you to estimate a latent growth model, what would lead you to estimate a residualized change model, what would lead you to estimate a cross-lag panel model, right? Maybe there is one, and maybe it's going to work in your particular case, but think about the conceptual model before you jump into the statistical model that you choose. That's kind of the bottom line here. And if you think about the economists versus developmental psychologists, developmental psychologists tend to jump right to the latent growth model. They learned. I had a friend who was an associate editor for developmental psychology, and there were all of these submissions where people had just learned how to estimate a latent growth model, and so they estimate a latent growth model, and they say, here you go, and aren't tying it to any sort of conceptual developmental model. So maybe these aren't the right ones for your particular purpose, but think about what is the right one. That's kind of the bottom line.
Greg, Amin has his hand up for a question.
Okay, Amin.
Yeah, I have a question. So for that to be average, doesn't it need to be divided by the number of years as well?
That's true. I've been a little bit loose in a number of things about these, right? So yeah, you do want to do an average in order to get a kind of an equal footing for the different measures across the equations. That's true. Now, the other thing I've been a little bit fast and loose with, when I talked about the z variables, I just talked about persistent z variables, right? But there are time varying z variables that that don't get differenced out, right? If z at age 5 is different from z at age 3, then change in z between ages 3 and 5 belongs over here on the right-hand side. And if that's unmeasured, then that could be a lingering source of omitted variable bias. The persistent unmeasured influences do get differenced out completely. And that's a huge benefit. So, you know, even though conceptually this B1 is the same as these B1s, you can argue this B1 is better because it's not biased by persistent, difficult to measure or impossible to measure z variables. So that's why in the childcare article, we ended up trusting this change equation most of all, even though we estimate this equation and we estimate this equation. We also throw in family variables from before age 3, other controls from before age 3. You know, we in the model section, there's another wrinkle that is probably too much of a complication to talk about here. But you know, suppose that childcare quality becomes more important later in early childhood, right? So suppose the B1 is bigger than the B1 at age 3. It's bigger at age 5 than age 3, right? Then you don't get this simple common B1 factor. You get a difference between the Bs, and the paper develops that model out of it. But that's kind of a minor point. You know, another question, and this relates to Amin's question, do you want a simple average of childcare quality birth to 5s, right? Maybe recent childcare quality matters more than childcare quality 3 years ago or 4 years ago. If that's the case, then maybe you want this childcare quality to be some kind of weighted average of past childcare quality, where you're giving more weight to recent childcare quality than more distant childcare quality, right? That's another wrinkle that you can take advantage of.
Can I ask another question?
Sure.
So in real life, we have to decide which model is best for what we are doing, right?
Right.
And then are there scenarios that like more than one model can be okay, or like can serve the purpose for like what I'm thinking that there might be some scenarios that like 2 different models can serve the purpose, right?
Well, I mean, you could have an article where you tested 2 different conceptual models, right? You know, the childcare article could have been, is a accumulation of inputs model more appropriate for thinking about the influence of childcare quality on cognitive development than an instantaneous change model, right? So you lay out both of them, you come up with very different estimated equations, and then you see which one seems to perform better in terms of explaining what you want to explain. You know, the other thing that I should confess is only people who have tenure have the luxury of insisting on being right rather than doing what referees want to see. Because, you know, whether something gets published or not, it depends less It matters less than if you have tenure than if you're a graduate student or if you're an assistant professor. So, you know, you might try this and people say, oh, you need a latent growth model, right? That exact thing happened to an earlier version of the paper that Paul is doing. And I could go on about this, but it didn't make any sense. It obfuscated what we were trying to do. But actually, we didn't do it. We just decided not to publish the paper. But you know, when a referee says, do a latent growth model, and the editor agrees that that's really what you should do, then you've got to do it if you want to keep going with that article at that journal, right? So life is filled with compromises, and that's one of them.
I have a question, Greg.
Sure.
For these types of equations, how do error terms fit in?
That's a good question. I left them out here conveniently, right? They, you know, you're always, I've kind of fudged the conceptual model and the estimation model, right? The conceptual model doesn't have error terms, but the estimation model does. You know, you get a, in the estimation equations, you get a difference in errors, right? When you have change on the left-hand side. But that typically is not consequential for trying to get an unbiased estimate of what the effective childcare quality is in this case. So that's not always the case, you know, and there are instances where the error term matters a lot more, but rarely. So first approximation, you know, with every piece of research, there are 10 different things to worry about, and you might be able to handle 5 of them. And this is pretty far down the list usually. Okay, so now that you've mastered this distinction between instantaneous change and accumulation of inputs, I want to do breakout rooms where groups come up with an example, you know, a practical example of an analysis that you could do with ECLSK data that reflected an accumulation of inputs kind of process. Okay, you know, you have an idea of all the outcomes, achievement outcomes, behavioral outcomes. You know what sort of things are measured, teacher characteristics, school characteristics, right? What would be an example of a longitudinal model that you could estimate with ECLSK that would be parallel, would be an application of an accumulation of inputs model? Right, and the extra credit do the same thing for an instantaneous change model, right? But first and foremost, come up with an actual scenario where ECLSK could be productively used to estimate an accumulation of inputs model. All right, I'm anxious to hear what you came up with. So let me share my screen with the slides, and we'll start with group 1. What's your example? Oh, and you went extra credit too.
Yeah, sorry, I didn't get to finish the extra credit one. I was just working on it. But
Quite all right.
So we were thinking that we might be able to observe the accumulation of reading score inputs from 2nd to 3rd grade based on the self-control rating. And so our first model I didn't write out all of the models, but basically our first model would have been reading scores at grade 3 equals the A plus B1, and then the sum of the self-control rating from kindergarten to 3rd grade.
Mhm.
And then plus B2, we thought we could maybe control for interpersonal skills, the rating about that. And we would look at that again from kindergarten to 3rd grade. And then B3 with our controls, and B4 with our unmeasured controls. So then the next one would be our reading scores at grade 2, and then equals B1, looking at self-control rating from the sum of the ratings from kindergarten to 2nd grade, and then looking at the interpersonal ratings, the sum from kindergarten to 2nd grade, and then measured controls, and then unmeasured controls. So when we subtract those two, we would have reading scores from 3rd grade minus reading scores from 2nd grade equals B1, and then the sum of the scores, the self-control ratings from 2nd to 3rd grade, plus the interpersonal scores from 2nd to 3rd grade, plus the B3 times the other controls, the measured controls, and then plus 0, since our unmeasured controls are canceled out.
Thank you. So you said sum of self-control, but you really mean kind of the prevailing level of self-control between the two tests, right?
Yes. Yes.
Okay.
Yeah.
I don't want to put words in your mouth.
No, I just didn't know how to explain it.
Yeah. Okay. That's good. And you want to say what your instantaneous change model is, just very briefly?
I was thinking maybe we could look at interpersonal skill change from kindergarten to 3rd grade based on the teacher's rating of internalizing behavior. So it would have been interpersonal skills from 3rd minus from kindergarten equals equals B times the internalizing behavior rating from 3rd grade minus kindergarten plus B2 times the change in our controls plus 0.
Okay, so you're saying internalizing behavior fluctuates somewhat over time,
Yeah.
and the interpersonal skills are going to be fluctuating along with it.
I think so, yeah.
Yeah. Okay. That's good. Any questions for Molly? Shall we move on to group number 2? Who wants to present 2?
I think it's me. So we decided that our outcome variable is to be looking at externalizing behavior problems in children ages 5 compared to children at age 3. Sorry, I'm looking at it and there's a typo. At age 3. So we have, you know what? That A is not supposed to be there. Totally ignore that. So we were thinking that SCS would be a big factor in externalizing behavior issues. We were debating whether or not SCS should go in the controls versus as part of the coefficient, but I think we ultimately decided that it's going to go in the equation because big changes in SCS would really contribute to more externalizing behavior problems, we think. Then our second variable that we included is family structure. That means if the parents are together, or if it's a single parent, or if they're separated. That's what family structure means. And then location change, for lack of a better word, is when they move, we're looking at, I think it was neighborhood characteristics. And then the last one, B4, is other controls. So some controls that we were thinking about, we would be looking at the change in these controls, but it would be the number of children in the household, so the siblings, parents' own externalizing behaviors, and then parental education. Yes, that is all.
Okay, so the key determinant, well, a key determinant, let's take SES. You're saying SES changes periodically, and it might be like unemployment, right? If a parent becomes unemployed, there could be consequences of that within the home, and kids might react to it, for example, right? Am I putting words in your mouth?
Yes, no, you put better words in my mouth. Unemployment is a much better way of saying, yeah, just basically drastic changes in SES.
Yeah, or it can be even like related to education. Like, let's say like when your child is 3, you just graduated from college, but and then when your child is 5, you probably have a job, and
Mm-hmm.
or or in the middle of like these 2 years, like you graduate from college and then you get a job, so suddenly your socioeconomic status changes a lot.
Okay, but this is really saying that these behavior problem changes are going to be affected by the average level of employment circumstances or average level of SES between the two measurement points, right? Otherwise, it's an instantaneous change model.
Yes.
Right? Okay. Okay.
I have a
I
question.
think there is a possibility for it.
Yeah. But this is all, I mean, and you can use, if you don't really know which is which, I mean, you can do a test because it's different models coming out of the accumulation of inputs and instantaneous change, right?
I had a question regarding the x's of accumulation of inputs model. Then would the x's always have to be a continuous variable, since you would need an average?
That certainly helps, but let's suppose you were thinking about a process that's affected by being in center-based childcare over a number of years, right? So every one of the years could be a 1 or a 0, but if you average across, say, 5 years, you get values of 0 and 1, but a lot of things in between. You get some 0.2s, 0.4s, 0.6s, 0.8s, right? So just because it's dichotomous at a point, if you're measuring it over a number of points, you can come up with a more continuous average measure between those points. Does that make sense?
Yes, thank you.
Okay, let us do group 3.
I can go. So after hearing what other groups said, we just I think I've at least realized our answers are not what we're supposed to do completely. But so what we were thinking is that for accumulation, we can use math scores or reading scores as a something that as an outcome, and then maybe an average sense of belonging as a predictor that we can average over time. So we just didn't think of enough control variables as other groups did, but if anyone can think of anything right now, just
Yeah, but the control variables are somewhat second order, right? The main point is that you're predicting
yeah,
test scores as a function of between 2 points as a function of how connected they are with school in between those points, right?
yeah, average of that, yeah.
Okay, that makes a lot of sense. Anybody in the group want to add to that? All right.
Actually, sorry, Greg. I actually had a question for you here because we were thinking about change and then the average and like how many time points, for example, in the data set that we have been working with. Yes, in this data set, it's 7 time points. So we were thinking like from K through 3rd grade. So that could be the change in the outcome variable, but then the average sense of belonging could be the 7 time points, right? It doesn't have to be 2 and 2.
Well, everything that you're averaging has to be between the 2 points where you're measuring the test scores, right?
Yes, for the for sense of belonging, which would be the independent variable. So there we would be like doing the 7 time points, but for the outcome variable, which would be the math test scores, are we doing the change would only be between the first and the last observation, or does it have to be right?
Yeah, so that's a great question. And you know, if you look at what I did on the board, the NICHD study, you know, had test scores not only at age 3 and 5, but also 4, right? So there could have been a middle test score, a cognitive score in there, but the model says no. The model says just look at 5 minus 3. So the model says throw away some of the information you have because it's not appropriate to include it. You know, if you've got an X variable where you want some average level of X between 3 and 5, and you've got 10 different measurements between 3 and 5, then by all means throw all those in because you want the best average measure possible, right? So in this case, if the model is telling you that the change should be beginning to end and the average in between change should be the average, you know, in one case you just want the endpoints, the other case you want as many data points as possible in order to get the X variable, the best possible average measure that you can.
Great, thank you.
Okay, now, you know, that said, latent growth models, which I can see we're going to have to relegate to a asynchronous little presentation, do take advantage of all the points in between to come up with a change measure. So, you know, it's possible to take them all into account. And I'll talk about that when I talk about the latent growth models. Okay, group
And
4.
also, we also like, yeah, for the instantaneous model.
Oh yeah, sorry.
Yeah, we think of maybe like if children's approaches in learning change from like, for example, fall to spring of kindergarten, then how would that affect their math scores or maybe reading scores? So we are predicting a change in math scores, like predicted by changing approaches to learning from one point to the other.
Okay, so, you know, there is a component of math scores or test scores that's very transitory, right? You've got to have a kid paying attention when he or she sits down to do the test. And if their attention is high or low, they could get a very different score, their motivation being high or low. I mean, I would think of a more persistent component of test scores as being the result of a much longer term process than an instantaneous change model would suggest.
Yeah, that makes sense. Good. Yeah. Thanks.
Okay. All right. Group 4. I can see groups didn't select a spokesperson. So
I
a
don't
volunteer.
mind.
I
I
can,
don't.
I can go. Oh, go,
Oh,
John. Go,
no,
John.
no. Fuko, do you wanna? Okay, I guess I'm gonna volunteer. All right, cool. So we decided to use math achievement as our y variable, and I guess the challenge for us was coming up with a series of independent variables that would relate to this dependent variable. So we have a little bit of a mix here. We have said that some of the frequency related math games done in the class between grades 5 and grade 3, plus the time for mathematics, plus whether or not a student was tutored in math in a categorical variable, plus unknown controls would be a way to measure achievement in the classroom. As you can see, we're kind of trying some things out. We know that the categorical variable will likely get canceled out when we're doing the final subtraction, but we think that the frequency of math games, the time for mathematics, and the measurable controls will still remain. And we were not able to get to the extra credit.
That's all right.
Right.
So tutoring could be a continuous variable, not just a 1-0 variable, right? They might get it in 3rd grade, but not in 4th grade. In which case, that would be different than if they got it in both 3rd and 4th grade, or got it in either 3rd or 4th grade, right? So you always want to make as continuous a set of variables as possible. So, tutoring might end up being more of a continuous variable than just a 1-0 variable. But, apart from that, this makes a lot of sense. Time on task, that's the time for mathematics, right? And in the data, the teachers report how much time they spend in math. Any other comments from this group?
It was tough going through the data set. There was a lot to work with.
Yeah, well, that's one of the challenges, to not get so tempted by all these variables. So, in thinking about a class paper, you could do worse than apply this kind of thinking to the class data set for estimating a simultaneous change, instantaneous change, or accumulation of inputs model. People have done that in the past. So, that's something to think about. Okay. I want to do just one more thing. Yeah, good job, group 4. I want to just point out a few things about the NICHD article itself. So this is a accumulation of inputs model. We start out with where we started out on the board, which is age 5, 54 months essentially, is a function of, here we distinguish early and late. Early is 0 to 3, late is 3 to 5. So it follows very much what we talked about on the board. So you've got childcare quality early, home quality early, childcare quality late, home quality late. These things, care add up to the accumulation of childcare conditions from birth to 5. The 2 home variables are the accumulation of home conditions from birth to 5, and then these child and family variables. And then we say, well, suppose that same thing was true at age 3. That's time S. And age 3, you only have the early components: early childcare, early home, and then these child and family components. And then we difference the two and get change in cognitive scores between 3 and 5 as a function of average level of care between 3 and 5. Average level of home conditions between ages 3 and 5. So it's exactly what we developed on the board. And then there's this point that the early and late coefficients might change over time, and then you get this somewhat more complicated equation. I'll let you dive into that if you want to. We said, okay, so our theory tells us that we want change on the left-hand side and not a residualized change model, with the lag dependent variable on the right-hand side, but everyone does residualized change model. So we'll do that if people want to see the comparison. This data set is really wonderful. Deborah Vandell devoted much of her career to it. It's followed kids through age 26 now. They were recruited at birth. They have an incredible amount of detail on early care, early development. So we want to know about this measure of childcare quality, the occupational record of the childcare environment, which they spent years developing and implementing. So these are really the key variables: early quality and late quality, 6 to 24 months, and then 36 to 54 months. And then there's home care. But those are really the two childcare quality variables that matter the most. And I wish they had presented standardized coefficients, but they don't. So you've got these cognitive scores generally with standard deviations that are around 15 points. So that helps interpret the coefficients. Start out with a level equation at 24 months. The only thing that you can look at in terms of childcare quality is early childcare quality. And you get, this is a Z-score, right? A 1 standard deviation change in childcare quality is associated with a 1.66 point change in test scores. If the standard deviation is about 15, that's about a 1/10 of the standard deviation. And then there are these various level equations for 54-month test scores where different variables are added in. You get late quality being associated with, by the time you add in variables you should be adding in, about a 1.2 point change in test scores for every standard deviation increase in childcare quality. Similarly, here, I think, not sure what the difference is. These might be, oh, I see, I'm sorry, cognitive scores and achievement scores, right? They both have standard deviations around 15, and you get, less than a 1/10 of a standard deviation change in both cognitive scores as well as achievement scores. But the preferred model is this simple change. You add in all the control variables that you should, and now you're getting an insignificant estimated effect of a standard deviation increase in late childcare quality, 0.59. Residualized change model, it's a little bit bigger, 0.86. It's really not that much bigger. Standard error is less, so it happens to be significant, but it's pretty small. That's cognitive score, achievement score, same kind of thing. 0.4, a little bit higher. And so as most of you pointed out, that score, which is a raw unit score with these achievement tests and cognitive tests, it's about a 0.04 standard deviation effect of a 1 standard deviation change in childcare quality. So that's not very much. And it's occasionally significant when you have it in the residualized change models. But policy relevance, think about it. First of all, we have no idea how to increase childcare quality. You might think, well, require credentials for the teachers, reduce class size in these centers, provide training, provide a curriculum. It would be very, very hard through policy to get a 1 standard deviation change in childcare quality. If you look at impacts of interventions trying to improve quality, if you get a 0.2 standard deviation, 0.25 standard deviation change in quality, that's a success. So, policy relevance, suppose you put the big effort into changing childcare quality and you get it up by 0.25 standard deviations. The estimated impact on test scores is now down to 0.01 standard deviation, right? It went from 0.04, which was an entire 1 unit standard unit change, down to a 0.25 increase. So, you could argue based on this article that worrying about boosting childcare quality is very irrelevant to the task of developing children's cognitive ability. Not a very well-received conclusion, in the developmental community. But I think they went ahead and published this article in part because the person I was working with, Peg Birchnall, is so widely respected. But also, there's so damn many numbers in this article that no one really understood the import of the implications. We tried to make it somewhat clear in the discussion section. We didn't try to mince words, but the early developmental community, it's not a hypothesis that childcare quality matters. It's more a philosophy that childcare quality matters. So it's really hard to bring evidence to bear against a philosophy. So one of my many battles that I have lost, but you win some and you lose some. What comments do people have, both to my diatribe against conventional wisdom of developmental psychologists? I really love developmental psychologists, don't get me wrong. I've spent a lot of time working with them. It just seems like there are a number of beliefs that they have that seem impervious to evidence. Next week, actually, we'll talk about other research that attacks one of their other cherished beliefs about the importance of early socio-emotional behaviors being every bit as important for later success in school as early cognitive development. But that's next week. So questions, observations?
I'm not quite sure if I missed this, but for the table, for the coefficients on residualized change models, how would you interpret that then?
You tell me. You know, if you believe in an accumulation of inputs model, that leads directly to this simple change model, right? And the interpretation, it's the you know, the B1 equaling the B1, that has a ready conceptual interpretation of a 1 unit change in childcare quality, right, being associated with 0.04 or whatever it is, standard deviation change. When you stick the lagged dependent variable on the right-hand side and it gets some coefficient, I don't know, it doesn't have a direct interpretation to either an accumulation of inputs model or instantaneous change model. Maybe there's some other model that it does correspond to, but I haven't seen any. And I should say, another view for residualized change, for lag dependent variable models, is that you really want, in this case, an unbiased estimate of the effect of childcare quality between ages 3 and 5 on age 5 cognitive development. You've got cognitive development in a residualized change model on the left-hand side, and you want to control for as many things as you can on the right-hand side in order to clean up an effect of childcare quality, right? So, you know, age 3 scores, and you should really put in, you know, a whole batch of age 3 behavioral scores, age 3 cognitive scores to control for as much heterogeneity as you can in order to clean up an effect of subsequent childcare quality. So that is a rationale, I guess, for a residualized change model. But if you go straight up with this accumulation of inputs model, the residualized change model has no direct sensible interpretation.
Just to follow up on that, so I see, so you're using the word effect. But then if we're looking at variables, like for example, if we look at the Eccles K, like if we're including variables that are all survey data, for example, and you can't be confident that you don't have an omitted variable bias, can you still use that word effect?
Yeah, that's a great question. So, you know, the accumulation of inputs model is a theoretical model that is a causal model, right? At a conceptual level, right? You're proposing that childcare quality causes cognitive test scores. You know, if you could come up with experimental data, kids were randomly assigned to different qualities, right? Then you'd have a pretty strong basis for inferring causation. If you don't have random assignment, but you have a technique, you know, think of the difference in difference or the regressionist continuity. Those aren't random assignment, but you can argue they're getting close, and they're getting close enough so that it's useful to think of your estimate maybe as coming close to what a causal estimate would be, right? And you know, here's where it gets a little tricky, because you could argue that, you know, this omitted variable bias controlling technique by differencing out disease, that's big, right? You're no longer plagued by the biasing effect of persistent characteristics. So you're getting getting something that you can argue is closer to a causal estimate. So, you know, the kind of mantra for developmental psychologists is, oh, we don't have random assignment, therefore we don't have causation, therefore we have associations, right? I don't buy. I mean, remember my heresy 101. You should aspire to causal estimates in whatever way you can, either with a random assignment design or with something that comes close to it, right? Because if you just take this, oh, it's an association, it's not causation, then you have nothing to say about policy, right? Policy is all about causal impacts. A policy is coming in and changing things, right? And in order to estimate an impact of policy, you need a causal estimate, right? So if you're saying, oh no, this isn't causal, then you should have no discussion section. And typically there are gigantic discussion sections where people kind of are unleashed to talk about whatever they want. But if you want to know the implications from the analysis itself, if you don't have a causal, arguably causal approach, then you're just stuck talking about correlations, and who cares about those? So again, I didn't promise to be unopinionated, but these are important things to think about.